Okay, welcome to welcome to lecture. We'll get started here in just a sec. And obviously we'll be picking up where we left off, talking about the wonderful world of titration. Let everybody through the door, or maybe. All right, let everybody in, hopefully. Here we go. I think everybody's coming in. Okay, I think, hopefully, there we go, everybody in. All right, so we are going to continue lecturing on titrations. This is where we left off. So just a little, got a few emails about experiment 7. So just to be clear, my intention was for you to attempt the calculations for experiment 7 and sort of have them attempted or tried so that when we get to lab today, and we are going to do, I think, experiment 7 today. And when we get to lab, you'll have some of that done, hopefully, or at least have thought about how to do some of those calculations. And I haven't decided yet, but I may just have you submit whatever you have. Again, if you haven't completed it, I just may have you submit whatever you may have. But we will talk about sort of the idea behind experiment 7 when we get there today, a little bit later. And then a little bit about sort of the idea of how you could use the equations and stuff to sort of figure out what they're calculating. But my goal is just to get you to kind of go through them maybe and start on them, get thinking about maybe how you would go approach those calculations and things of that nature. So if you haven't completed the calculations for experiment 7 or in the middle of the calculations or like you did something and maybe it's okay or not really sure. It's okay. Okay. So you'll obviously have an opportunity today during lab to do those calculations. We'll probably take some time, obviously, like we've been doing at the beginning of the lab for you to kind of either double check your calculations, make sure they're sort of in the right area, before we sort of watch the video and stuff like that. Okay. So, the goal was just to kind of get you looking at them before you show up to lab, maybe get some ideas in your head as to maybe how you would approach it. And again, like I said, we'll talk a little bit about maybe how to approach it, what you want to be looking for, and sort of the idea behind at least part A and B. I think part C is pretty self-explanatory, but we'll talk about that at the beginning. Okay. Any questions on that? Okay, so what we have been talking about is titrations and titration curves. And we first talked about a strong acid and a strong base titration. And remember that in a strong acid, strong base titration, the curve does look very similar to what we have here. So maybe we'll go back and take a look at that just to make sure. Oops. Come here. There we go. So this is the titration curve that we were looking at for, again, a strong acid and strong base titration. And again, just for sort of orientation purposes, as we talked about, the sodium hydroxide is up in the burette, the acid is in the beaker, the flask, and you're obviously adding base to the flask. So you're adding base to the acid. And again, we do see this typical sort of S curve, and that's because at the very beginning of the titration, before we add anything, the only thing we have in the flask or the beaker is the strong acid. So we see a low pH as what we would expect, since that's the only thing that's in the flask. And obviously, as we start adding some base, we see a gradual sort of rise in the pH here as we add the base. And as we talked about, when we get close to that equivalence point, we usually typically will see a pretty good sort of jump in the pH as you reach the equivalence point. So again, as we reach the equivalence point, and we talked about, it does go sort of vertical, kind of straight up, and you typically will see, again, a sort of jump in pH to the equivalence point. And again, usually you'll see a jump after the equivalence point in terms of the pH when you look at a curve. And obviously the equivalence point, as we talked about, is the point in a titration where you've added, especially an acid-base titration, you've added basically equal moles. So the number of moles of acid will equal the number of moles of the base. And that's basically your definition of the equivalence point. As I mentioned before, typically you'll see that jump after the equivalence point, which is what we see up here. And then usually it will level off in terms of the pH. And obviously once you go past the equivalence point in this type of titration or setup, you're essentially just dumping strong base into your solution. So you get an increase in hydroxide ions, a decrease in H plus ions, and obviously the pH goes up at that point because of that. Now really in most titration curves, there's sort of like 4 points in terms of the curve. The first point is usually the initial before you add anything. So in this example here, that would be like at 0 amount of sodium hydroxide added. And in this particular titration, because the only thing you have in the flask is a strong acid, and because that's a strong acid, you could immediately go into the pH equals minus the log of the H plus concentration because you have the concentration of that strong acid. And because it's a monoprotic acid, that H plus concentration is the same as the concentration of the whole acid. Now, once you do start adding some sodium hydroxide in this particular example, like we talked about, you do need to do an ice table. So once you start adding all the way up to before the equivalence point, you do need to do an ice table. And that ice table does need to be done in moles, as we talked about. And the purpose of that ice table is to figure out how much strong acid will still be there. And that's because before the equivalence point, the moles of the strong base you're adding is going to be like the limiting reagent, which means it will get used up. And you will need to do an ice table in moles. After that ice table in moles, you do need to convert it to molarity afterwards, and you'll have the molarity now of your strong acids. So in this red section, as we talked about, it does require one ice table, again in moles, and the purpose of that ice table is, as we talked about, to basically figure out the concentration of your strong acid after you've added all of the base that you're going to add. When we hit that sort of that green circle area there, where that dot is at the equivalence point, that is, as we've talked about, when the moles of the acid and base will equal each other. And because this is a strong acid and strong base, the only thing that we will be left with at that point is a salt. And we'll be left with a salt that came from a strong acid and a strong base. And as we know from talking about salts, that means that that is going to be neutral, which means in this type of titration, you really don't have to worry about any type of calculation at that point. The pH should be 7, which is what we see in that table. Once again, you go past the equivalence point in sort of that purple area that's circled in this type of titration. Again, you pretty much have excess amount of strong base being added. So what that means is when you do an ice table, which you need to do, also again needs to be done in moles, you need to figure out how much strong base is left over. Because remember, once you pass the equivalence point, and if you keep going and adding the strong base, basically you're just adding base, basically, right? And what you need to figure out is the base now becomes the excess reagent, your strong acid is the limiting reagent, and all of the strong acid will get used up. And that means that you will have an excess amount of your strong base left over. And again, after the first ice table in moles, you could convert back to molarity, figure out your new concentration of your strong base, and that will allow you to get to the POH and then to the pH. So remember that what we just talked about in terms of those 4 sort of sections is specific for this type of titration here, which is our strong acid, strong base titration. We then talked about another type of titration, which is our weak acid, strong base titration. The setup here is very similar. The sodium hydroxide, which is your strong base, is in the burette. The beaker there, which has your weak acid in it. So again, here you're adding your strong base to your weak acid. And you do see a similar curve, maybe not as steep as we saw on the other one. Also, we see it kind of starts a little higher up on the pH, but again, this area not as steep, but we still see that vertical rise as we reach the equivalence point. So this problem is a little bit different, and it's a little bit different in the sense that at the very beginning, if we kind of look at the 4 areas of this titration curve, at the very beginning, the only thing that we have in the beaker, as we can see here, is the acetic acid in this example. And because acetic acid is a weak acid, you cannot go right into the pH equation. You do have to do an ice table with molarity and the Ka value. So it's basically a Ka problem starting out over here. So really right about here, you got a Ka problem happening. Again, you'll do an ice table with molarity because you have not added anything. Excuse me. You haven't added any base to it, so you could use the molarity that's given. That would be done with x's. And obviously, when you solve for x, x would equal the H plus concentration. And then obviously from the H plus concentration, you can calculate the pH. So again, because here we're starting with a weak acid, it is slightly different how you start the calculation. And again, that's why it's important to understand sort of what you got going on. Now, once you do start adding some base to this situation, all the way up to the equivalence point, is going to require you to do one ice table at least. That ice table, when you are done with it, needs to be done in moles. And afterwards, you can convert it to molarity. But once you are completed that first ice table, no matter what the deal is, you will always be left with, as it says there in the blue, you will be left with a buffer. So that's sort of a buffer region of the titration. And that's why we also see that, you know, it's not sharply rising here. You know, it's sort of maintaining its pH along there because really you're creating a buffer. And that's kind of like the experiment we're going to do today. You're kind of creating a buffer from this reaction of a weak acid with a strong base. And what that means is once you're done with the first ice table, you do have 2 options. Because you will always hit a buffer at that point, you can either go right into the Henderson-Hasselbalch equation, which is probably the easier move, or you could do a second ice table and ignore the Henderson-Hasselbalch instead. So just like when we talked with buffers, you have 2 options, ice table or Henderson-Hasselbalch. But again, probably the Henderson-Hasselbalch would be a lot easier. So again, you can see this part of this type of titration is very different than the other titration we were talking about. Now, once we get to that green area where the equivalence point is here, what's going to happen is the same thing as before. We will use up all of our acetic acid in this example. We'll use up all of our sodium hydroxide as well. And we will be left with just a salt. And that salt in this particular case is sodium acetate, which is right here. Now, unlike the salt in the first titration, this salt comes from a weak acid and a strong base, which means the part that comes from the weak acid will actually go through hydrolysis. So when you're at the equivalence point in this type of titration, you actually need to do 2 ice tables. The first ice table is to figure out the concentration of your salt. The second ice table, which should be done in molarity, the first one should be done in moles, the second one should be done in molarity. The second ice table, which should be done in molarity, is a hydrolysis problem like we talked about when we talked about salts in the previous chapter, where it will react with water, and when it reacts with water, it will actually produce hydroxide, which means it will be basic at the equivalence point in this type of titration. And it also means that you need to probably figure out the Kb value using like Kw. And you can get the hydroxide concentration. And from the hydroxide concentration, you get the pOH and then the pH. So really at this part of the situation here is really a hydrolysis problem. So you can see, you know, you got 3 different sort of problems happening here. And then obviously once you go past the equivalence point, the same situation is occurring. You're basically adding a more sodium hydroxide. The sodium hydroxide in this example becomes like the excess reagent. So in the red area of this graph, it does require, again, an ice table done in moles. So hopefully you can kind of see a pattern. First ice table in most cases should be done in moles when you're doing titration, except if you're just starting and haven't added anything. But once you do that first ice table and you can convert it back to molarity, what you will have is basically two things at that point. You will still have the salt that we just talked about in that red area, but you'll also have this sodium hydroxide left over, which again is a strong base. So in comparison of the sodium acetate, which can act as a base, and the sodium hydroxide, which is a strong base, at this point in the titration, the major contributor to the pH would be the strong base, the sodium hydroxide. So if you remember, that's the point in the titration where we ignore the contribution of the salt and we look at the sodium hydroxide or the strong base, and whatever the strong base may be, as the source of the pH that we see. And because it is a strong base, that pretty much means that you have the hydroxide concentration, and that would allow you to get the POH and then to the pH from that. So again, it does require one ice table. Purpose of the ice table in the red area is to figure out the concentration of your strong base, and then you can obviously get your OH minus and your POH and then your pH. Any questions on any of that we talked about, I think, last time? I think that's what we talked about last time. Sounds sort of familiar. So I think we went through just kind of fake examples here. So why don't we just try one with sort of real numbers and give you a chance to try it. Let's say, let's say we want to know what is the pH after 23 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid. Ka value again for acetic acid is 1.8 times 10 to the minus 5. All right, so I want you to take a few minutes and see what you come up with in terms of the pH, and then we'll talk about it. Okay, let's take a look, see how you're doing. Just move some stuff out of my way here. Okay, so obviously we're doing a titration. So obviously, as we've been talking about, we do need a reaction. So a reaction is going to be our acetic acid plus our sodium hydroxide. Going to give us some sodium acetate and some H2O. Now, obviously, this titration, so as we talked about a number of times, we do need moles. So again, same type of calculation we've done before. So if we take 0.023 liters, which is our 23 milliliters converted into liters, times it by the molarity here, moles per liter of our sodium hydroxide, which is 0.1, we will end up with 0.0023 moles of sodium hydroxide. We would do a similar calculation for our acetic acid. It would be 0.025 times, let's see here, 0.025 times 0.1 gets us 0.0025. So that's going to be our initial, 0.0025 moles, 0.0023 moles, and 0. Now, as we talked about last time, you can really use your ice table to figure out where you are in terms of the titration. Again, remember that this is what we started with. This is what we are adding. And again, the moles of what we're adding is less than what we started with. So that tells you you are before the equivalence point. Again, because if they were equal, you would be at the equivalence point. So whatever you're adding is less than, so you're before. That also means because we are before the equivalence point, the change is going to be the sodium hydroxide in this case. So we're going to go minus 0.0023, 0023 plus 0.0023. That means at equilibrium, we will end up with, we got there 3 zeros and a 2, it looks like. So 0.0002 moles. This would be 0 and 0.0023 moles, right? So at this point, we do want to convert it back to molarity. So the first table here in moles. Afterwards, we want to convert back to molarity. So we got our 25 and 23 is 48 milliliters of total volume. Again, when we pretty much add these guys together, it gives us 48 milliliters, which means we want to divide by 0.048 liters. And that does give us 0.00417. We'll go to 0.00417 molar. And on the other side, 0.0479, it looks like. Any questions on that so far? Okay. So again, if you're not sure what you're dealing with at this point, your ice table could help you. We see that at this point, we have acetic acid there, and we have sodium acetate there. We actually just made a buffer. Hopefully you can recognize that. Again, very similar to what you need to do for today's experiment. We reacted a weak acid with a strong base. The strong base is gone. It left us with a buffer, which, by the way, is what we would expect to happen in this type of titration before the equivalence point. That's your buffer region, right? So we would expect this to occur. That means that we could do another ice table, or again, probably the easier move, just go into our Henderson-Hasselbalch equation. The pKa in this case would equal minus the log of the Ka value. 4.74. That means that the pH would equal 4.74 plus the log of our base, which is our sodium acetate, so our 0.0479, divided by our acid, which is our acetic acid, obviously, 0.00417. And if you do all that, maybe like a pH of 5.80. Any questions on that calculation, where any numbers came from, any of those things? So just to kind of give us an idea where we're at, I'll put it back up in just a sec. So at 23 milliliters, should actually move this to the right spot. That puts us right here. We came in at 5.8, which is between 5.6 and 6.12. So we are good. We are just before the equivalence point, kind of like where we're rising in this area here. I would think we're somewhere about that area, I think, in terms of it. Any questions on that particular calculation or how we got those numbers? So again, it is really good practice to convert it back into molarity at that point. Truth be told, though, just a reminder that technically speaking, if you are using the Henderson-Hasselbalch equation, you could just leave it in moles and put it into the Henderson-Hasselbalch equation. You will get the same because when you divide the base divided by the acid, the 1,000 milliliters cancel out of both, so everything becomes the same. If you are to go on to another ice table, you definitely should have it in molarity. But I say that there's other calculations that you do definitely need in a molarity. So usually it's really good practice to convert it back to molarity after that first ice table. Any questions on any of that? Then let's talk about the last type of titration here. And this is a titration of a strong acid with a weak base. So the setup here is a little bit different. In this setup, in the burette, is actually the strong acid. So the HCl would be up in the burette. Down here in the beaker, or the flask, would be our weak base. So in this particular case, we are adding the strong acid to the weak base. And that means it looks just like the curve we just saw, except that it's kind of upside down. So let's talk about why it's upside down. And let's start out with what happens when we start the titration. So again here, before we add any hydrochloric acid to it, at the start, no acid added. Again, the only thing that we have in that beaker would be like NH3. We would just have our weak base, which means this essentially is a KB problem, which means you just take the weak base, like NH3, you add some water, right? It's going to accept the H plus and make NH4 plus and OH minus. You would use an ice table here. You would use your molarity and X's. So molarity zeros, minus X's, plus X's. Molarity minus X, X, and X. You would solve for X in this case, just like a normal KB problem. And just like a normal KB problem, that would equal not the H plus concentration, but it would equal the OH minus concentration, which obviously will get you to your POH and then to your pH in that case. So very much like sort of the last example, except that we were starting with a weak acid in the last example. This time we're starting with a weak base, and that is because and why we actually see the pH start higher, because when we're starting, we actually have a high pH because we're starting with a base, and as we add the acid, we should see the pH start to drop, which is what we see here. That then brings us to the next sort of part of the titration curve, that kind of second part that we've been looking at in all these. And that part consists of where we start the titration over here, again, to before that equivalence point. And at this point, we are adding some HCl to it, which means we do need a reaction. So in this case, we would do a reaction between, say, the HCl and the ammonia. Gets us a little ammonium chloride. I'll just separate them. Or again, you could put them together if you like, but we'll keep them separate for this. So again, you would want to do this ice table in moles. So I'm going to just make up my number like I did before. I'm going to assume that I had 4 moles of this guy. And again, this is what I'm starting with in the flask or the beaker. This is what I'm adding. So if I am before the equivalence point, what I am adding is less moles than what I started with. So we'll go with 2 moles that I made up. This would be 0. Change would be -2 in this case, -2 plus 2 moles, which means when you reach equilibrium, you got none of the HCl left over. You got 2 moles of this guy. You have 2 moles of this guy. Just like we did in the previous one, you could take the total volume and convert it to molarity. But more importantly, what we see at this point is we have some NH3 left over. We also have some NH4 plus left over. This should also be a hint that that is a buffer. So again, here we generated a buffer by starting with a strong acid and a weak base to generate this buffer. And that is, again, in this region, just like in the previous one, a buffer region, which is why, again, the pH kind of maintains a little bit before it kind of significantly drops in that range. The difference is in the first one, the buffer was an acidic buffer. In this one, the buffer is going to be a basic buffer, but it doesn't matter because you could go into your Henderson-Hasselbalch equation and get your answer. So much like the last one, we're going to end up with a buffer anywhere from starting the titration to before the equivalence point. And again, the only difference is it's going to be a basic buffer in this particular case. Any questions on that? Now, when we do get to that equivalence point, also going to be very similar to the last one we just saw. So we'll go with purple, why not? So right there on our equivalence point, that dot is going to happen when we have equal amounts of those guys. So at the equivalence point, our HCl in this case, plus our ammonia, giving us our ammonium chloride in this case. So same idea, you do need to do an ice table in moles. Again, we'll start with 4 moles of this guy. And if we're at the equivalence point, we should have 4 moles of this guy and nothing of this guy. Change, you can't mess it up. It is 4, the magic number here, right? 0, 0, and 4 moles. You also notice I've been ignoring the chloride, and I've been ignoring the chloride because it is a neutral salt, so you don't have to worry about it. So there's a question as to what you would use for this last one. You would probably want to use this one, so I'll answer your question one of 2 ways. You'd probably want to use this one here, which is the Henderson-Hasselbalch equation. The one that you're actually referring to, you could also use, but it's not the pH. That gives you the pOH, which is the pKb plus the log of the acid divided by the base. So alternatively to the one on the bottom here, this one, you could use that version of sort of the Henderson-Hasselbalch equation that we talked about. But remember that that doesn't give you the pH, that gives you the pOH. So you still need to subtract 14 from that, right, to get to the pH. So you could absolutely do it this way as well. but you would have to, again, do that extra step of sort of subtracting the 14 to get to the actual pH, because that's probably what you're going to be calculating in this case. Again, remember that you can use the Henderson-Hasselbalch equation there on the bottom, no matter if it's acidic, basic, it doesn't really matter the pH of the buffer. The key is you just want to make sure you have the pKa value and the base on top are acid. But you could technically use this version of it. But again, a reminder, sometimes people forget that it's not the pH, but it's actually the pOH that you would be getting. Other questions on that? All right, so at this point, we would convert it back to molarity just like normal. And what we're left with really is a salt here, right? Ammonium chloride. And remember that the chloride, as I just mentioned, is a neutral salt. But this ammonium did come from ammonia. I'll say that right. The ammonium came from ammonia. And ammonia is a weak base, which means this NH4 plus will go through hydrolysis. So much like what we saw in the previous one, at the equivalence point, the salt will go through hydrolysis. It's going to act as an acid, which means it's going to donate its H plus over. And when it does, you'll get NH3 plus H3O plus. So a couple of things here. We would do an ice table. We would use the molarity that we got right here, right? So that molarity would come here. These guys would be zeros. These would be X's. But most importantly, when we see this, we should automatically know that it's going to be acidic here because we're producing H3O plus. We also know we need a Ka value, which most likely you will have a Kb value for this guy here. So you got to make sure you have that. In this case, you would solve for X. X would equal the H plus concentration, and then you could go into the pH. So very much like the other one, you will hit a hydrolysis problem at the equivalence point. The difference is it's going to be an acidic hydrolysis problem where you produce H plus, and the solution should be acidic at this point. And again, that's what we see here. If we come through here at the equivalence point, in this particular example, 5 point, whatever it says there, 28, which is definitely acidic. So remember, salt is just an ionic compound. So something like this, where you have a positive guy and a negative guy together, cation, anion is a salt, right? And remember, as we talked about with salts, it's basically production is produced as a result of a reaction, typically with an acid and base. So it's just an ionic compound. And chloride coming from HCl, which is a strong acid, means that Cl minus is relatively weak and will not go through hydrolysis, sometimes referred to as a neutral salt in that case. The ammonium part is also a salt. It's just that part will go through hydrolysis. Technically, the salt is the ammonium chloride together. All right, so let's talk about the last part of this titration curve. And the last part of the titration curve. So after the equivalence point, just like in the other titration, you're just dumping all this HCl in there. You know, who cares the indicator change, right? You're just going to dump it in. So what happens after the equivalence point in that case is we have, again, our reaction. Again, we're going to do moles. So again, I'm going to use my 4 mole example. And again, this is what we started with, and we're adding our HCl. So since we're after the equivalence point, the HCl that we're adding should be more than what we started with. Again, that's going to cause the change to occur that the ammonia in this case now will become the limiting reagent. So we'll end up with -4, -4, plus a 4. And that will be 2 moles, 0, and 4 moles. Again, just like everything else we did after that first table, convert it back to molarity. Now we're left with HCl, and we're also left with ammonium. Now, again, just because you have two numbers here, this is not a buffer. They are not related to each other. But we do have two things. We have our salt here, which will go through hydrolysis, right? Just like we just saw. And it will act as an acid. But we also have the HCl, which is definitely a strong acid. So just like what we did in the previous titration curve, at this point in the titration, we ignore the contribution of the salt, because although it is going to be producing H+, the HCl, which is a strong acid, pretty much just needs to go for a swim, and it's going to produce a lot of H+ really quickly. So what that means is at this point, we do have the concentration of HCl, which is essentially the concentration of H+, which means you could go right into your pH equation at that point. So this type of titration where we're adding a strong acid to a weak base is pretty much identical to the titration curve that we saw previously. And there really, again, is those four parts. The difference is we're starting with a base and sort of ending acidic, as opposed to starting acidic and ending basic in the previous titration. But to start this one, again, the four sort of parts, it's a KB problem to begin with. So ice table, X is solved for X. That gets you the OH minus concentration and the POH and then to the pH. Anywhere from the start of the titration to before the equivalence point, you need to do, again, at least one ice table, and you will always end up with a buffer. The buffer will be basic in this case. And then you can go into the Henderson-Hasselbalch equation, or again, you could do a second ice table if you don't want to do that. At the equivalence point, just like the last one, we will have some hydrolysis happening. So you will end up with a salt. That salt will react with water, and that salt will produce H3O+, which is acidic. Means you Ka value you need, but you need to do two ice tables, one to get the concentration of the salt at equilibrium, the second a hydrolysis problem where the salt reacts with water and produces H3O+, and you need to figure out the concentration of the H3O+, and you could go into the pH equation. And then lastly, in that fourth quadrant there, that's red, you will basically have a lot of strong acid just being dumped in there. And because it's a strong acid, it's going to be the major contributor to the pH. So you just need to do one ice table to figure out the concentration of the strong acid, and then you could get to the pH. Any questions on this type of titration curve? Okay, so obviously you do need to be able to figure out the pH anywhere along any of these curves. And what I was talking about the other day, and it's really important, is if you understand that really there's four parts to each of these titrations. If you understand what type of problem you should be in and you should be doing, it makes the calculation a lot easier than sort of just jumping into it. And that does come from understanding where you are in the titration, what type of titration it is, because again, as I mentioned last time, if you have in your head what type of problem you should be doing, you know, that usually will kind of focus you down the right path. Again, a lot of people get in trouble because they just jump in. They really don't have an idea what's going on or where they are in that titration curve. And they just go, I'm just going to try to do it based off of numbers and like formulas. And that's usually where we get people just constantly using the Henderson-Hasselbalch equation everywhere and getting the wrong answer. Any questions on any of that? All right, then let's continue on our big titration day here. It's a big titration example, right? So 4 different answers, 4 different parts, 30 minutes. All right, I'll give you like 20, 25 minutes to start working on it. So we have 4 different parts here for this titration. The Ka value is given to you on the bottom. So we want to know what is the pH at the initial solution. So that's before we add anything. So just so we're clear, the sodium hydroxide is being added to the nitrous acid. So the nitrous acid is in the beaker, sodium hydroxide in the burette. Then we want to know what is the pH after you added 80 milliliters of the sodium hydroxide. Then we want to know what is the pH at the equivalence point. And finally, what is the pH after 105 milliliters of base has been added. So why don't you take like 20 minutes or so and get started on it, and then we'll go through some of the parts here before we finish up for today's lecture. So give it a go, see what you come up with. Again, do try to work it out yourself because you will eventually have to. So make sure you work through these problems here and see how you're doing. All right. So I'm going to be quiet for a while. Yeah. So and go for it, work it out, and see how you do. Okay, so hopefully you got at least through A, maybe B, hopefully working your way through this. So since we're getting towards the end of this lecture, let's at least start with looking at A, maybe get into B here, and then obviously you can continue working on it, and we'll finish up the rest of them tomorrow. But let's first take a look at part A. And first off, though, when we want to sort of figure out what's going on here, again, always a good idea to have an idea as to what you're dealing with. So definitely HNO2 is a weak acid, and we know that because we do have a Ka value for it. So we're doing basically a weak acid and a strong base, which is sodium hydroxide titration. So again, our sodium hydroxide is up here, our HNO2s here. And we should also visualize in ourselves that sort of curve that we saw. It looks very badly drawn there. Try maybe make it a little bit better, maybe not. So it should kind of look like this in terms of our curve. So initially what we're going to be starting with is just a weak acid in this titration. So again, you're here at part A. And again, just knowing what type of titration it is and where you're at, you should already know that you should do pretty much a Ka type problem like we've done before. So that's where we'll start here for part A. So in part A, we have our HNO2, and it was 0.1 molar. And again, the Ka value 4.5 to the minus 4. And again, since we have not added anything, we're just going to do our basic weak acid that's going to break apart. We're going to use the molarity again because we haven't added, so we don't have to change it to anything else. These are going to be zeros, going to be minus x, plus x, plus x, which means at equilibrium 0.1 minus x, x, and x. Any questions so far on that? So this is really just a Ka problem like we did in whatever chapter that was, 14 maybe. This is going to go into our Ka expression, which would be our products over our reactants. And that will equal our Ka value of 4.5 times 10 to the minus 4. That will give us x squared over 0.1 minus x equals 4.5 times 10 to the minus 4. You can make an assumption here if you like, and you can assume that x is equal to 0. And again, if you do that and you check it, I think you get something like 6.7%, which technically means it is bad. So I'm just going to save a little bit of screen here and not do that. But again, if you did the assumption, remember that you should check it because technically in this case, it is bad and at 6.7%. So basically what we need to do is multiply the bottom here to the other side, and that's going to give us x squared equals 0.000, one more zero, yep, 45 minus 4.5 times 10 to the minus 4 x. Putting everybody together, x squared equals, no, let's try that again, x squared plus 4.5 times 10 to the minus 4x minus 0.0000045 equals 0. This is obviously going to go into our x squared minus b plus or minus b squared minus 4ac divided by 2a. Obviously, we put all of our values in, and just give you some of the numbers here. That will get you minus 4.5 times 10 to the minus 4 plus or minus. If you put all the numbers in the square root, you get something like 0.0001802. 1802. You take the square root of that, you get 0.0134, all divided by 2. That's going to give us 2x values. X is going to equal 0.00648. or it will equal minus 0.006693, it looks like. So obviously we're looking for our H plus, which is equal to X. So it can't be the negative number. So that means that our H plus concentration in this case, to open up, is 0.00648 molar, which means the pH is minus the log of that. And that's going to open us up, I believe, with a 2.19 pH. Any questions on any of those steps? So again, just basic Ka type problem like we did before. You could try the assumption. You should check it. Again, technically wrong, even though I know if you kind of just blew through that assumption and did it, you probably ended up with a value very close to it. But based on us, it would technically be wrong because it was above 5%. Any questions on part A? Now, part B, we're actually going to start the titration here. So we want to know what the pH is after we add 80 milliliters of the sodium hydroxide to it. So in part B, we are going to get a reaction. So B, we added 80 milliliters of our 0.1 molar sodium hydroxide to gain old 100 milliliters of 0.1 molar NaOH. So again, here we're going to have a reaction. So that's going to be our, nitrous acid would be good. HNO2. HNO2 plus our sodium hydroxide going to get us sodium nitrite and some water. So since we are doing this titration, we do need to do it in moles. So you should grab a calculator. Let's see. Here we go. So for our HNO2, we have 100 milliliters, which is 0.1 times 0.1 gets us 0.01 moles. 0.01 moles. For our sodium hydroxide, we have 80 milliliters, which is 0.08 times 0.1, 0.008 moles here. And 0 here. So a reminder that if you're not sure where you're at, this is what we started with. This is what we're adding. And what we're adding is less moles than what we started with, which means we are before the equivalence point here. That also should tell you that you should absolutely know how this table is going to end up. And we'll just make sure you do, hopefully. The change is going to be the sodium hydroxide because we're before the equivalence point, minus 0.008, minus 0.008, plus 0.008 on this side. Going to get us at equilibrium. 0.002 moles. Nothing here, and 0.008 moles. At this point, we can convert back to molarity. Total volume is, we started with 100 milliliters in the beaker. We added 80 milliliters, so that's 180 milliliters, which means we should divide each of these by 0.18 liters. And that is, again, is our total volume of the acid we started with divided by the base, or the total volume, which would be 180 milliliters. And that gives us 0.0111, 0.0111. And on the other side, 0.008 divided by 0.18, 0.0444. Any questions so far on the ICE table? Again, hopefully before you got to the point of the calculation, because you know you were at before the equivalence point in a titration of a weak acid and strong base, you should know that when you look at your ICE table at this point, we have HNO2 left, NaNO2. These two guys here are again a buffer. So again, we created a buffer here, which is what we would expect to happen at this point in the titration. And again, this is why it's good to know where you are, so you could make sure that your calculation does make sense. So since we do know we should have a buffer here, we have a buffer here, you can go into the Henderson-Hasselbalch equation, pKa plus the log of the base over the acid. Our pKa value in this case minus the log, and what was that, 4.5, I think, right? 4.5 to the minus 4. And that would get you 3.35. And that means that the pH would equal 3.35 plus the log of the base. So again, the sodium here, the one that doesn't have the extra hydrogen, is our base. So this guy would want to go on top. And our acid would go on the bottom, which is our nitrous acid. So that makes sense. So 0.0444 divided 0.0111. Take the log of it and add 3.35 to it. Gets us a pH of 3.95 at this point in the titration. The 4.5 times 10 to the minus 4 should be the pKa value, I hope, unless I looked at it wrong. I think so. Right there on the bottom. Any questions on that calculation there? So again, we see that we did get a buffer, and that's what we would expect to happen. And like I said before, you could have done another ice table instead of that part. Any questions on any of those steps? So if you haven't finished part C or D, I would ask that you please kind of go through that tonight so you have them kind of ready to go. And tomorrow during lecture at the beginning, we will obviously finish parts C and D. That way you can check to make sure that you hopefully did it correctly for those parts. Any questions on any of that there? Okay, so we're going to have lab. We're going to do experiment 7, which is buffers. And it's pretty much what we just did there. We're going to create a buffer from a reaction of either a weak acid with a strong base or a strong weak acid, say that again, weak acid with a strong base, or a strong acid with a weak base. Yeah, so again, we'll go over for sure C and D. So think about the titration curve, and again, sort of where you are and what should be occurring at that point. Okay, we will start lab, and we'll start 5 after. So we'll do 305. We're going to do experiment 5 as well. Okay. All right, I see your questions. Just give me a second. Otherwise, I'll see everybody in about 10 minutes or so. Yeah.